The Internet of Things, also known as IoT, is a system of interrelated computing devices, machines or objects that have the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. In this seminar, Mr. Peter Waher, editor of IEEE 1451.99, explores the requirements behind the use of smart devices, including autonomy, security, and interoperability across domains. Mr. Waher also discusses the standard of using smart contracts and certification that will have a significant impact in the upcoming era of Industry 4.0 and smart cities.
So first I want to introduce Industry 4 to you. So this image that you see here is a typical image to illustrate the four different revolutions, industrial revolutions. The first was mechanical power. Obviously, it was a great impact. And then we have mass production, the second revolution. Then came automation, obviously greatly improving productivity. But it has a limit. So automated processes are typically pre-planned, and there is just so much you can anticipate when you're building a factory. To build a new type of industrial process, you must make the process adapt to its surroundings. You cannot pre-plan a modern process. And this is the fourth industrial revolution. How do we make processes adapt automatically? So comparing the previous automated process with the upcoming fourth generation of industrial process. First, traditionally a process is seen as an isolated, closed and sealed off process owned by a single, say, factory or industrial plant. In the fourth revolution, the boundaries will be erased, integration will be autonomous and automatic, and will be cooperation over domains to optimize processes. Instead of centralized processing, we will have decentralized processing. Instead of pre-planned decisions, we will have systems that make decisions on demand. This is called ad hoc, and autonomously, without human intervention. Another key aspect from a technological point of view is that a fourth generation process, the key here is interconnectivity between different processes automatically, as opposed to local sealed intra-connectivity. To make this possible, obviously, if you have two different kinds of companies wanting to cooperate, there is only one efficient way to do this, and this is to build on standards. New types of standards need to evolve to make this happen. Otherwise, we end up with proprietary solutions, and proprietary solutions become sealed already from the start. So key motivating factors for this revolution. Europe has long felt that it has lost its competitive advantage, obviously to Asia, to China in particular, but also other countries, and sees a need to optimize and revolutionize industrial processes, to reindustrialize the West again, so to say. And to do this, new types of processes are envisioned. Not only better or more productive, but processes also need to be sustainable, consume less energy, reduce downtimes, breakdowns, and also in some cases use limited resources very efficiently. Some examples. I'm sure most of you have heard about predictive maintenance. This is perhaps one of the first things companies try to achieve. Instead of letting processes break down, processes automatically diagnose themselves to predict when something needs to be done, and so proactively makes decisions to optimize the process and limit downtimes. This is very common. But others include logistics. You might have heard of Amazon, for instance. They started this automation of the logistics process. And so one way to do this is to involve third parties in the logistics and in the transportation sector to optimize flows of goods. Other things might be mining, for instance. Mining is very expensive, and one day of a water pump being broken costs many millions of dollars. So a huge cost involved in not having a mining operation optimal. But furthermore, in transport in general, transport is not the same from one day to another. You need a system that can adapt number of vehicles, for instance, to number of goods being transported. Agriculture, as you know, in many areas of the world, resources are limited. So how can you use every drop of water, for instance, as efficiently as possible? In construction sites, those of you who work in construction know that it's not one company anymore doing construction. Often a construction site consists of very many companies that have to use and reuse co-usage of resources to efficiently build whatever they are building. Now, optimization has been a key word here. So there are different things you can optimize. For instance, we have talked about adapting to current demand. There is no point in creating more goods and services than is being required, for instance. We have talked about distribution of limited resources, like water from a river in a desert area, for instance. We have talked about increasing productivity, obviously, for competitive reasons, or lowering costs, increasing lifetimes, not only human lifetimes, but obviously, but device lifetimes and operation lifetimes, reducing energy consumption in general. What do these examples have in common? And that is the coin. It's all about saving money, because the more money you can save, the more things you can do with the same amount of money. So it's not about greed, it's about better usage of your assets. And so part of the Industrial Revolution is monetization of resources in general, technological terms, because the money aspect is a very efficient optimizer. If you can monetize every resource in a process, it will automatically become better optimized. We did an example already in the 90s where a big steelworks came to us and asked if we could optimize their steelworks, and we obviously said we don't know, because we don't build steelworks, but we said that unless you know how much energy is consumed in every part, there is nothing you can do. So they agreed in installing 600 electric meters in this steelwork. And just by installing these 600 electric meters and distributing the energy consumptions to the corresponding 600 departments, the energy costs plummeted. As soon as people had to start to pay for what they were responsible for, that part of the process started to become optimized. And this is a general finding, I believe, that if you can monetize resources in a process, it will optimize either by human ingenuity or through automatic means, which is part of Industry 4. That is, building technology that allows free markets for resources, so that devices can make deals. There was big expectation 10, 15 years ago about what Internet of Things would give us, and one company after another had greater expectations. Finally, now when we've seen what happened, we've realized that only half or a third of these expectations were reached. The key point here was that originally everyone thought there would be a big reuse of devices. If there were devices installed in society, everyone could use them to optimize processes. This never happened. So consider this, for instance. If you invest all your money in devices and you install them in your society, what incentives do you have to allow others access to these devices? If you allow others to access your devices, two things will happen. First, it will degrade your own system performance. And secondly, they can build a competing service without having to invest in devices. There are absolutely no incentive to share anything in Internet of Things by default. But an economic feedback built into the technology that allows device owners to get an economic feedback for usage will solve this problem. So it will allow companies who invest a lot in devices to allow others access to them, and if they access the devices, they get paid. And this is a great enabler and a requirement actually for sustainable development. Now, IoT is particularly vulnerable from a cybersecurity point of view. We all know that the security landscape changes rapidly, but IoT solutions are costly and should operate over long periods of times, often invisibly, often without human operators or any visible cues that these devices are attacked. There are also larger number of devices, and what's more is that the devices now are connected to the physical world. Previously, you could hack a computer and make a lot of nuisance, but now you can actually attack physical objects, physical processes and systems. And finally, very few consumers pay for security, and you don't see security. You can see a lack of security. You see when your device is perhaps hacked, but you cannot see security because nothing is there to see. So we have to ask ourselves this question. What are our options? Do we have to seal all our systems to make them secure? Then we have to throw away the vision of a smart city and Industry 4 because they require openness and interoperability. Or are we, as William Barr says, expected to accept the vulnerabilities of open systems, that open and interoperable systems are invariably vulnerable? Or is there a way to create open and interoperable and also secure systems? And this is what I've been working on for too long time. But in order to achieve this, again, standardization is important. Security, especially cybersecurity, the security of a system is not more secure than the weakest link. It doesn't matter if 99 of 100 does a great job, if 1 in 100 does a poor job. And in order to have 100 out of 100 working to an acceptable level, the only way is to have a standard that enforces a minimum requirement and a certification of devices to make sure that everyone that is being sold is kept to this standard. Currently, there are within IEEE 3 efforts that I participate in that work on cybersecurity for the smart society and Industry 4. These are the ones. Now, let's talk about certification of smart devices. Interoperability is the key word in Industry 4. Interoperability requires devices to have expected behavior. It's not sufficient to test, for instance, an electrical meter or a temperature sensor, that it measures, for instance, temperature to a certain degree of exactness. If the temperature sensor doesn't know how to behave in the network, it's useless anyway. So this digital behavior needs to be certified also, perhaps to some extent even more important than the physical behavior. For autonomous decisions even to be made, humans are not even involved. And so all these certifications, these claims about behavior need to be digitally available and understandable by devices. This is very important. It's no longer humans that will consume this certification letter. It's other types of devices. So they have to be digital, they have to be understandable. Again, standards come in. They must never be tampered with fraudulently. So they need to be protected cryptographically. And claims that are made must be verifiable somehow. Otherwise, we cannot build a smart society. So obviously, you have a lot to do here. And obviously, standards bodies also. Now, consider certificates. Most of you are aware of certificates, digital certificates on the web, for instance. If you go to a safe website, you have a digital certificate that proves that you're on the correct server, for instance. This is a standard called X509. It's part of a series of public key cryptography standards. It's a very, very simple model, very efficient in what it does. But for those that don't know how it works, you have different certificate authorities that certify that the claim is true. For instance, a domain name is belonging to a certain computer. And you have a chain of certificate authorities ending in a root. And if you trust the root, then you can trust the chain and therefore also the certificate, therefore also the claim. Now, such certificates are very difficult to use for what we attempt to do in Industry 4 and smart cities. They're very limited, very difficult to extend. They're very efficient in what they do, but they're simply difficult to use for what we need to do. So consider this. What kinds of things do we need to certify for a smart device? We have the traditional physical aspects of a meter or a sensor, for instance. Obviously, electric or electromagnetic properties or radio properties. We have already talked about communicational properties and conformance to standards. These perhaps are easy to understand. But the new types of devices need to be able to make agreements. We have contractual information that is necessary. If we're going to choose a temperature sensor out of 1,000 for our purpose, autonomously, we need to know things like lifetimes and warranties and whatever usage requirements there are. If there are fees involved, how much does it cost to use a device and so on. These types of things also need to be certified. And then you have more complex aspects that cannot be solved by a simple yes-no question. For instance, how mature is the technology? How secure is the technology? What is the performance? It's not a yes-no. We need to convert these more complex questions into numbers that can be used for actionable or operations. Now, one certificate authority cannot do all these things. They cannot certify all these things. It requires expert knowledge. For instance, a cybersecurity expert might not know anything about temperature sensing or IoT maturity, etc. So we need a way to provide claims and certifications where different certificate authorities or different authorities provide parts of the answer. And there is a concept that works for this purpose, and it's called a smart contract. Some of you might have heard it in terms of blockchain, but smart contracts is not limited to blockchain. The difference between a smart contract and a certificate is that it can have different parts. It works more or less like a digital version of a human contract between humans. It can have different roles, different parts. There is a machine-readable aspect which is extensible. So you can have any type of subject you like. You can have any type of complexity in the information that you certify. Also has a human-readable part, so you can combine the two. And the authenticity is provided by trust providers, or as we want to call them also, notarius electronicus, that attests to each signature. to make sure that it's legally binding. So I wanted to introduce a very simple example. This is perhaps not the best example, but it's an example that I hope many of you have already tried. Are you familiar with this Qualsys SSL labs? If you're developing services, perhaps you are. So this is a service that helps you evaluate the security of a website by analyzing its cryptographic and certification properties. And it works very well as an example for how a certification authority for these more complex evaluation tasks might look like. So you go to this site, you enter a site you want to analyze, and it gives you first an overall rating. This overall rating is actionable. A device who understands this can have a rule saying, I will not communicate with anyone that has a grading C or below, for instance. That's a very simple thing to implement. So it's actionable. But then it can be broken down. It has details, so you can get information about what strength and what weaknesses it has. It goes into even more details. You can go into details about certificates used. It can go into details on what protocols are being used. It can even go into ciphers. Now, obviously, now you start to see that analyzing the security of a single site is quite complex. You have to have a lot of experience and knowledge in how to do this. And it's not expected that anyone can do this and also be expert in something else. This is a full-time profession. So a certificate authority is required, especially if you go into, like this page, declaring what kind of vulnerabilities you have. So they test for all known vulnerabilities and certify if you have it or if you don't. And this is very, very important information, obviously. Now, how would this look in a digital manner? So consider this example. Say we want to do something similar in an autonomous fashion. What you saw before was a human report. Now we want to enable something similar in a digital setting using smart contract. So in 1451/99, which is a standard for smart societies, there is a smart contract that allows us to encode this kind of information in a secure manner. It is based on XML, which is much easier to work with than abstract syntax notation 1. The point is that abstract syntax notation 1 was very popular in the 80s. It generates compact binary encodings of information, but it's exceptionally difficult to work with and extend. While XML is quite easy, you can use Notepad or similar tool just to edit it. So it's human readable. So you can encode more or less any type of information that a human can generate. But it still allows for the same kind of cryptographic algorithms to secure these documents, made sure they are not manipulated in any way, and also verifiable. Now, if you remember the report, this example here will show how such a report might look like in a smart contract based on XML. First, there is a header that gives the system awareness of how long time, this time 3 months, for instance, this contract is valid. It can be archived. It's a requirement to archive this contract after, then for 2 years, optionally extend it for 1 year for bookkeeping. Then it has a machine-readable section. Those of you who know XML knows that XML is well defined by using namespaces. So anyone who controls a namespace can control the syntax of the XML. In this case, IEEE IoT sensor data namespace is used to encode the information in the report. This is just a simple example with the overall rating B at the top and then going into more and more details. So this can be consumed by a machine. Then comes roles. So a smart contract, instead of having only one authority, you can specify any number of roles, in this case a manufacturer and an authority role. So this report will be signed both by the manufacturer and an authority validating the claims. It will have parts. So roles are the abstract roles. Parts are the entities that sign the contract, in this case the manufacturer and the authority. These are physical entities with physical or network identities. 1451 also has the concept of a legal identity. So in order to make legally binding agreements, each participant in the network has a legally binding, cryptographically proven identity. And basically it's a separate XML representation. Those of you who are interested in cryptography might recognize the algorithms used. Otherwise, it's a collection of key and name values like this, first and last name and personal number, address, etc. And then the client signs it, binary, with the algorithm specified up here, and the server or the Notarius Electronicus signs it also to make sure the reader can validate the claims. A contract also has parameters that can be set, obviously. Think of a rental contract or similar. And then comes a human readable section. We don't have to go through this, but it states more or less the same thing as the machine readable section. Then comes a part of signatures, cryptographic signatures of the parts that have agreed in this case. You might not be as interested to read what these numbers mean, but they are mathematical proofs that the corresponding entities have agreed. And finally, the Notarius Electronicus signs this. And this includes information that the state is approved. This means the Notarius Electronicus has made sure not only that the machine-readable part is valid syntactically and validates, but also that the human-readable part and the machine-readable part are the same, so they are legally binding. So I will conclude here just by giving a reference to this standard for smart societies, 1451.99, IoT harmonization. As you can see here, it has a lot of different subjects that relate to communication and interoperability in smart societies and Industry 4. I've only touched now briefly on identity discovery, legal identities, and smart contracts. That are important, but it includes other things like interoperable communication and localization, distributed transactions, different types of security like peer-to-peer communication, end-to-end encryption, etc. All the way to monetization and economic feedback that we also mentioned. And so with this, I wanted to conclude my talk.